Engineers and designers use CAD, computer-aided design software, to create detailed blueprints that specify the dimensions, materials, and structural integrity of the project. Before actual fabrication begins, a simulation is carried out to test the design's feasibility. Advanced software is used to simulate structural behavior under different conditions, such as load, stress, and environmental factors. Once the design is finalized, the steel plates or sheets are cut into the required shapes using flame cutting. Oxy-fuel cutting, plasma cutting, or laser cutting methods are employed to achieve precise cuts. After cutting, the steel pieces often have rough edges and irregular surfaces. Grinding smooths out these imperfections, ensuring that the pieces fit perfectly during assembly. Fabrication involves assembling the cut and ground steel pieces into the desired shape. This process includes bending, rolling, and drilling as needed. The components are temporarily held together using clamps or tack welding before final welding is done. Welding is one of the most critical steps in steel fabrication. It involves permanently joining steel components using techniques like MIG, TIG, or arc welding. Skilled welders ensure strong and durable joints, following precise welding procedures to maintain structural integrity. To verify the strength and durability of the welded joints, destructive testing is performed. This involves applying extreme force or stress to a sample weld to check for weaknesses. In addition to destructive testing, non-destructive testing (NDT) is carried out to detect defects without damaging the structure. Methods like ultrasonic testing, magnetic particle testing, and radiographic testing help identify internal flaws in the welds and steel components. After welding and testing, a dimensional check is performed to ensure that the fabricated structure meets the original design specifications. Measuring tools such as calipers, micrometers, and laser measuring devices are used to verify accuracy in dimensions, alignment, and overall geometry. To prepare the steel surface for painting or coating, sandblasting is conducted. This process removes rust, scale, and impurities, creating a clean and roughened surface for better adhesion of protective coatings. Sandblasting is performed using high-pressure air mixed with abrasive materials such as silica, steel grit, or aluminum oxide. The level of abrasion depends on the type of coating required. The final step in steel fabrication is the erection of the steel structure at the construction site. The fabricated components are transported and assembled using cranes, bolts, and additional welding as needed. Proper alignment and securing of the structure ensure stability and safety. The process involves lifting heavy steel members into place, positioning them according to engineering plans, and fastening them securely. Temporary supports may be used to maintain stability during assembly. Rigorous inspections are carried out to confirm structural integrity, ensuring the completed framework meets engineering and safety standards before final handover. The melting process is the first critical step in producing ductile iron pipe, transforming raw materials into molten iron of suitable composition. The primary raw material used is scrap metal, predominantly shredded automobile bodies, which are delivered by tractor trailers and moved to the melting area via magnetic cranes. The melting occurs in a cupola furnace, a tall cylindrical structure that operates continuously. The cupola is charged with alternating layers of scrap metal, coke, and limestone. Coke, a byproduct of coal, serves as the primary fuel source, generating the extreme heat required to melt the metal. The addition of limestone aids in the removal of impurities by forming slag, which rises to the surface and is skimmed off. To maintain the high temperatures necessary for efficient melting, hot preheated air is continuously blown into the coke bed through two air inlets at the base of the cupola. As the metal melts, It picks up carbon and sulfur from the coke before exiting the furnace through the tap hole. The molten iron flows into a large ladle, where sulfur is removed by adding lime, an essential step in producing ductile iron. The desulfurized iron then moves into a holding vessel called a forehearth, which maintains its temperature and composition before further processing. Casting is the process where molten iron is shaped into ductile iron pipes using the Delivad centrifugal casting method. This method ensures uniform thickness, strength, and durability while allowing for efficient large-scale production. The process begins when molten iron of the correct composition is transferred from the forehearth into a pouring ladle. This ladle holds enough molten iron to cast multiple pipes before needing a refill. The casting machine operator then inserts a sand head core into the bell end of the cylindrical steel mold. These sand cores, made from a resin-bonded sand mixture, help shape the pipe's bell socket where joints will later be fitted. Once the mold is prepared, the pouring ladle tilts, directing molten iron down a chute into the mold's bell end. The mold assembly is then moved along rails as iron continues to pour, filling the entire pipe length. Centrifugal force created by the rapid spinning of the mold pushes the iron outward, ensuring an even wall thickness. The peened surface on the inside of the mold helps the iron adhere properly, preventing splashing and defects. As the iron cools and solidifies, lighter impurities, such as slag and gases, are forced to the inner surface of the pipe, where they have minimal impact on performance. After the pipe fully solidifies, it is extracted from the mold, and the remaining sand core is broken up and removed. The hot pipe is then placed on rotating rollers to maintain roundness and straightness before moving to the annealing stage. Annealing is a critical heat treatment process that enhances the ductility, strength, and toughness of ductile iron pipes. After casting, the pipes are still brittle due to rapid cooling in the mold. To correct this, they are transferred to a natural gas-fired annealing oven, where temperatures reach 1,750 degrees Fahrenheit at the entry point. As the pipes move slowly through the furnace, the temperature gradually decreases to 1,350 degrees Fahrenheit in the cooling zone over 35 to 45 minutes. This controlled cooling allows the graphite nodules in the iron to form properly, ensuring the pipe achieves the desired mechanical properties before further processing. Quality control is an essential part of the ductile iron pipe manufacturing process, ensuring that each pipe meets strict industry standards for strength, durability, and dimensional accuracy. Quality checks occur at every stage of production, from raw materials to the final product. The first quality checkpoint occurs during melting, where samples of molten iron are taken at multiple stages, before and after desulfurization and after magnesium treatment. These samples are analyzed in a spectrometer and infrared analyzer to verify chemical composition and detect unwanted elements like tin, copper, and chrome. After annealing, each pipe undergoes visual inspections under flashlights and floodlights to identify any surface defects. Pipes are then weighed to ensure they meet minimum weight requirements. If a pipe is underweight, it is downclassed or scrapped. A hydrostatic pressure test is performed on every pipe, where water is pressurized to 500 psi for 5 seconds to confirm structural integrity. Additionally, mechanical tests are conducted, including tensile strength, yield strength, elongation, and impact tests. The Charpy impact test checks toughness at both room temperature and -40 degrees Fahrenheit to ensure the pipe resists brittle fractures in extreme conditions. Microstructure and ultrasonic velocity testing further verify the pipe's internal consistency. Only pipes that pass all tests are marked with their class, date, and manufacturing details before moving to the finishing stage for cement lining and coatings. The finishing process is essential for enhancing the durability and corrosion resistance of ductile iron pipes. After annealing and inspection, each pipe undergoes lining and coating procedures to protect it from both internal and external environmental factors. The first step in finishing is the cement mortar lining, which protects the interior of the pipe from corrosion and prevents the buildup of deposits that could reduce water flow. Before application, special caps are placed on the pipe's bell and spigot ends to ensure proper lining coverage. The pipe is then rotated at high speeds while a pre-mixed batch of Portland cement mortar is fed through a long trough extending to the far end of the pipe. Centrifugal force distributes the cement evenly along the inner wall, forming a uniform protective layer. A high-speed spinning station further compresses the lining, removing excess water and ensuring a smooth, durable finish. Once the cement lining is applied, the pipe moves to the coating stage, where a thin asphaltic seal coat is sprayed onto both the interior and exterior surfaces. This coating helps retain moisture in the cement for proper curing, while also providing an additional layer of corrosion resistance. After coating, the pipes are bundled and left to cure for at least 24 hours to ensure proper adhesion and durability. A final visual inspection is conducted before the pipes are loaded for shipment, guaranteeing that only high-quality products reach customers. Latest technology utilizes advanced machinery for precise, efficient ECR fiber production. ECR glass fibers are specifically engineered to enhance the durability of composite materials, making them crucial in industries such as construction, automotive, and aerospace. Flexibility in ECR glass fiber manufacturing allows customization of products, including woven bands and assembled rovings, to meet diverse industry needs. This adaptability ensures optimal performance across various applications, from automotive to construction. Woven bands, made by interlacing individual fibers, are known for their strength, flexibility, and ability to withstand various mechanical stresses. These bands are widely used in applications that require reinforced structures, offering a high degree of design adaptability. Assembled rovings, on the other hand, are bundles of glass fibers that are carefully twisted together to form a unified strand. Consistency ensures uniform quality, reliability, and performance across all products. Chopped strand mats provide strength, durability, and versatility in composites. Superior quality ensures high performance, durability, and reliability, meeting strict industry standards and customer expectations. Coatings and linings are protective layers applied to pipes, preventing corrosion, wear, and damage from environmental exposure and mechanical stresses. Carbon steel piping is frequently subjected to harsh environments where corrosion, impact, load, and soil stresses are common challenges. Fusion-bonded epoxy involves applying powdered epoxy, which is heated to form a durable, corrosion-resistant bond. Layer coatings consist of multiple protective layers, such as epoxy primers and polyethylene, to provide enhanced corrosion resistance and durability. It is often applied to external surfaces of the pipe, offering a highly effective protection solution. Extruded layer coating involves applying a molten polyethylene outer layer over a primer and adhesive, using an extrusion process to ensure uniform coverage, strong adhesion, and enhanced protection against environmental damage and corrosion. Medium-density polyethylene, MDPE, is a durable, corrosion-resistant material often used as an outer layer in coatings. It provides excellent protection against mechanical damage, environmental stress, and corrosion, enhancing the pipe's longevity. Liquid epoxy lining creates a smooth, durable, corrosion-resistant internal pipe coating. Cement mortar lining involves applying a thick, durable cement layer inside pipes, offering corrosion resistance and structural integrity, especially for water transport. The hot piercing mill is a key process in the manufacturing of seamless pipes and tubes, particularly in the steel and metal industries. This process is primarily used to convert solid billets, chunks of metal, into hollow tubes, a crucial step for industries such as oil and gas, automotive, and construction. The process begins with a solid cylindrical billet of metal, typically steel, which is heated to a high temperature in a furnace. This heating process makes the metal more malleable and easier to work with. Once heated, the billet is transferred to the piercing mill, where it is pierced to create a hollow section. The hot piercing mill operates through a mechanical piercing mechanism, often using a rotary piercing process. In this method, the heated billet is placed between two rollers that apply pressure. A piercing mandrel, which is a pointed tool, is driven into the center of the billet. The intense pressure combined with the high temperature causes the metal to deform, forming a hole in the center of the billet. This hole is enlarged and shaped as the billet moves through the mill. The hot piercing mill's main advantage is its ability to produce seamless pipes without welding, making it ideal for high-pressure applications where welded joints might fail. After the piercing process, the hollowed tube may be further reduced in size or elongated through elongation or rotary extrusion. In addition to the physical shaping of the metal, the hot piercing mill ensures that the surface of the pipe remains smooth and free from cracks or flaws, which is critical for maintaining strength and durability. Straightening is an essential step in metalworking, particularly for pipes or tubes, to ensure they meet precise dimensional and aesthetic standards. After a forming process like hot piercing or rolling, the material may exhibit bends, twists, or warps due to internal stresses or uneven cooling. Straightening corrects these deformations. The process typically involves passing the material through a straightening machine, which uses a series of rollers or pressurized rolls to apply force at various points along the tube. These rollers gradually reshape the metal, restoring it to a straight configuration. Straightening is crucial for ensuring the material is uniform in size, ensuring it can be efficiently processed in further steps like coating, cutting, or welding. Material for pickle refers to metal that is prepared for the pickling process, where it is treated with an acid solution to remove surface oxides, scale, rust, or other impurities. The pickling ensures a clean, smooth surface. A coating bath is a process where metal items are submerged in a solution, typically for coating with protective materials like zinc. Cutting in manufacturing involves dividing the metal into specific lengths or sizes using mechanical methods such as shearing, sawing, or laser cutting. After processes like piercing or coating, the material is cut to the required dimensions for further processing or shipment. Cutting ensures that the finished products are accurately sized and ready for applications in industries like construction, automotive, and energy. Material for straightening refers to metal products, typically tubes or pipes, that require correction of any distortions or deformations that occur during earlier stages of manufacturing. After processes like extrusion, rolling, or piercing, the material may exhibit bends, twists, or warps due to internal stresses or uneven cooling. These deformations can affect both the functionality and appearance of the metal, making it essential to straighten the material before it progresses to the next manufacturing step. The straightening process is vital for ensuring uniformity and consistency in the final product. Materials requiring straightening are often passed through a series of rollers, which apply controlled force at various points along the length of the material. This helps to eliminate bends and restores a straight form. The straightening process may be performed hot, while the metal is still heated or cold, once the material has cooled down, depending on the type of metal and the degree of deformation. The quality control process of seamless steel pipes includes several stages: visual inspection for surface defects, dimensional checks for accuracy, and non-destructive testing (NDT), like ultrasonic or eddy current testing to detect internal flaws. Additionally, mechanical tests such as tensile hardness and impact testing are performed to ensure strength and durability.